Hello, my name is Zachariah Brown, and I'm a fifth-year PhD student here in the Plasma Dynamics and Electric Propulsion Laboratory at the University of Michigan. Most of my research takes place in this big behemoth behind me known as the Large Vacuum Test Facility, or as we call it, LVTF. This 9-meter long by 6-meter diameter chamber is used to simulate the vacuum of space as we test the cutting edge in electric space propulsion technologies. In particular, my research focuses on a technology known as the Hall effect thruster. But before I get into the details of my research, let's head on inside and take a look at one in action. Here we are inside LVTF. It's a little dark right now, but why don't we brighten things up with some plasma? This right here is a Hall effect thruster in action. This device is accelerating ions to several thousand meters per second to provide the force necessary for space vehicles to travel from here to Mars or even just keep in station in orbit. My research focuses on how electrons travel from this bright central cathode to the cylindrical outer anode, where it collides with a gas and creates the ions before they are accelerated downstream. The process looks something like this.
The Hall thruster has an axial electric field shown by the green arrows. Electrons born at the cathode travel up the green arrow towards the positive anode. We apply this red magnetic field in the radial direction to trap the electrons along these field lines, so it takes them much longer to reach the anodes. This improves efficiency and is fundamental to the operation of these devices. Now we might expect a trickle or a small drizzle of electrons to then reach the anode. What we've seen through experimental research is it's actually a torrential downpour of electrons.
Now we believe that this anomalously high electron transport from the cathode to the anode can be explained by some form of plasma turbulence. Now, we can test this using experimental methods. So let's cut to a picture of the Hall effect thruster running from its side. Now we can see here that we've set up some probes on the far downstream plume, and we're going to inject those up into the acceleration region where the ions are accelerated, and we believe this plasma wave starts. We can use this probe to infer the frequency, the wavelength, and the amplitude of any waves that might be inside this device. And by using some plasma theory, we can back out what effect this has on the electron dynamics. You can think of it almost as if a surfer is crashing on top of a wave, and that in the same way the electrons are crashing on these plasma waves and then falling towards the anode.
If you're interested in learning more about my project or the other interesting projects happening at pepl, please visit our website below. Thank you.